Starting from lecture 2, we'll talk about supervised learning. And in the first part, we'll talk about a few methods um, such as linear regression, polynomial regression, and penalized regression techniques. Right, so for this topic, many of you should be familiar with the topics here because many of you have taken applied linear regression. So remember, for linear regression problems, we discussed before, you have some data, and you have some output y, right? The output y is related to maybe just one single inputs or one single feature, and maybe it's related to multiple features. Right? In the first case, we call it simple linear regression. In the second case, we call it multiple linear regression. So here, suppose we're talking about multiple linear regression. Right? That means you have multiple inputs. Here, in our case, we have n inputs. Right? Also, we call it n features. Right? They are the same thing. Sometimes we also call it predictors. Right? There are many names for this. And the function is in the linear form. Right? That means function f, it's a function of these input features x1 to xn. So we use the bold letter x to represent the vector that contains x1 to xn. So f is a function of the x vector, and it's in the linear form. Right? It's beta 0 plus beta 1 x1 plus into beta n xn. Right? This is the multiple linear regression. And here, beta 0 to beta n, they were called the model's parameters were coefficients. Okay, so given the data, that means you're given the x, you're given the y, which is f of x. But you want to determine the values of beta 0 to beta n. So you have n plus 1 coefficients to determine. And sometimes we can also think about this as a vectorized form. Right? That means we let beta be the vector of betas. So we use the bold fonts beta to represent the vector that contains all of the n plus 1 betas, the n plus 1 coefficients. And x is the vector where the first element is 1. Then it has all of the n inputs features. Right? So just add the number 1 in front of all of the n features. And we call it the bold x vector. And it's basically, we can rewrite equation 1 as a vectorized form, which is a dot product. That's beta dot x, right? Here, the beta and x, they are vectors. And also, we assume they are column vectors. Right? So for dot product, we can write it as a beta transpose times x. So beta transpose is a row vector, and x is a column vector. Right? So the result will be row vector times column vector. That will be a single number. That's a scalar. All right. So and also, we also call the beta 0 term, right? In machine learning, we also call it the bias term, right? It basically means the intercepts, right? It's evident from simple linear regression, right? That means it's the intercept term, right? In machine learning, it's also called the bias term, right? So now we should be familiar with the vectorized form of a linear regression problem, right? Or linear regression model. Right. Remember, the setting is we have a bunch of data. Right? Suppose we have capital N data. Right? Capital N data, that means we have n such data pairs, x1, y1, x2, y2, x3, y3. We're talking about a multiple regression. So each of these xi, it actually contains n features, the first until the nth. Right? So each bold xi is actually a vector of the n features of the nth data. So we use xi1, xi2, and xin to represent the input features of the ith data. Y1 is simply the output value of the ith data. Right, so all of these are our data. So based on this data, we can actually estimate the parameters beta or the coefficients beta. And the most often used method to estimate beta is the least square criterion. Right? Basically, it gives you a cost function. Based on its cost function, you can try to minimize the cost function. Right? It will give you a set of solutions for beta. Right? For this particular cost function, we're going to see is actually the residue sum of squares. Right? The residue sum of squares it means the squared sum of the difference between the data y and this is the predicted data. Right? F of xi is actually the output value predicted by your linear regression. Yi is the true output value for the ith data. Right? So yi minus f of xi is the difference between the true outputs and the predicted outputs. And then we look at the squared sum. F of xi, if you replace f of xi using equation 1, so you can rewrite the first part, right? You can rewrite this part, you can rewrite this part as this. Right? They're the same thing, right? Using equation 1. All right, so this is the residue sum of squares, right? The yi minus f of xi, right? It's actually the residue, right? So you can think about these are the data, for example. These are the y's, and you have a linear regression line. It's here, right? So this is your prediction corresponding to the x. Okay, this is your y. So corresponding to this x, this is the predicted value, that's f of xi. This is the true data value, yi. Right? So the difference between this, right, it's the residue. Right? Same thing, this is the residue here for this point. So it's the residue sum of squares. So we can use this as the cost function, and we minimize this residue sum of square, and that particular beta will be called the least square solution, right? And it's also equivalently, it's also the same as minimizing the mean square error. The mean square error is simply the residue sum of square divided by n. Right? So minimize residue sum of square, it's same as minimizing the mean square error. Right? Because there's just a divide, it's divided by the mean square error is obtained by residue sum of squares divided by a constant n, which is the number of data points. Right, so now we know the least square solution is basically minimizing the residue sum of square or the mean square error. So we can also put everything in terms of matrix and vectors. Right, so we can get a solution more easily. And we can also get the so-called normal equation in matrix form. So for this purpose, we first need to define the X matrix. Right? The X matrix is also the matrix related to your input features. Right? So it's a m by m plus 1 matrix. So this is n, this is m plus 1. Right? The first column of this X matrix, they're all ones. Right? They correspond to the one here. You add additional 1, right? Because your beta 0 term, that's obtained from beta 0 times 1, right? For the dot products. So beta 0 times 1, that's beta 0. So the first column are all ones. Right? Second column is the first feature. Right? We call this x11, the first subscript means which data point you're looking at. We're looking at the first data point. First row is about the first data point. Okay, so that's 1, 1, 1, 2, right, and 1, n. Right, so for the second row, that's 2, 1, 2, 2, 2, n, right, and so on. So the second row contains all of the features related to the second data point. Second row means the second feature for all of the data points. Right, so this is until xn1. Right, xn2 for the nth data point, what's the second feature? For the nth data point, what's the nth feature? So you can see this has n rows. That means we have n data points, and it has n plus 1 columns. It's all of the n input features and plus 1 column of ones. So it's n plus 1 columns. So that will be our x matrix, and y denotes the vector of all of the output values or target values, right? So just y1 to yn. So based on this x and y, we can actually find the beta that minimizes the residue sum of squares. And we call this particular beta beta hats. That's the beta that minimizes the residue sum of squares. It actually can be obtained by x transpose times x, take the inverse times x transpose times y. Right? This is actually called the normal equation. Right? Or you can rewrite it this way, right? X transpose x times beta hats equals x transpose y. Right, so this is the same thing as this. Right? We call this a normal equation, or we call this normal equation. So it gives us a way to calculate the optimal beta. We call it we write it as beta hats. Right? Optimal here means the one that minimizes the residue sum of squares, which is also called the least square solution. Right? The beta hat here is actually called the least square solution. All right, so we have actually talked a lot about this during applied linear regression. Right, so this is actually a revisiting of the knowledge we discussed before. All right, so let's look at examples. So whether this is true, right? Let's clear everything here. And let's move to the first example here. For this example, we don't use some real data. We just make up some data which look linear. Right? So here what we did, here we create some x data, right? We can try to figure out what this x means. So first, the numpy.random.rand, right? This is a very important, random is a very important package related to NumPy. Right? NP is NumPy. Right? Again, we actually imported NumPy right at the beginning. Right? So you should be familiar with this. We first import NumPy. Right? SciPy, we don't use it. You can delete this, right? But it's fine. We just put it here. For pandas in this package, in this lecture note, we don't use it, but we just put it here. We will use the sklearn.linear model for regression purposes. Also, this is something new. We explain what this is. So we import this polynomial features class from the sklearn processing package. Okay, so we'll talk about what this means. We also import the matplotlib package as usual, and we do a matplotlib inline, so you can see you have all these plots here on the same page. And this is something new. Or from matplotlib.pylab, we also import the RC-PARAMs class, right? So for this one, right, this is RC parameters. We want to change the size of the plots, right? Then we can use RC params to do that. Okay, this is something new. There's two things: polynomial features and RC params. All right, so here what we're doing is we generate rands. This rand function generates uniform random numbers between 0 and 1. Right, so here we just generate 100. This is 1D array. The result will be 1D numpy array. You generate 100 uniform numbers between 0 and 1. Then you multiply it by 2. So x is actually uniform random numbers between 0 and 2. And here we're trying to create a function or create some data that looks linear, right? So you can see here, it's actually a linear function, 4 plus 3 times x. So this is a linear function. And what we're doing here, we add some noise to the data point. For each data point, we add some noise. So rand n, this is the way to generate normal random numbers with the standard normal random numbers, right? That means the mean is 0, the standard deviation is 1. So to generate 100 standard normal variables, right? So we use the standard normal variables as the noise for this data points, right? So if think about if you don't have this noise, right, that will be strictly a linear line, right? Y equal to 4 plus 3x. But with this noise, right, you can see it's not too far away from linear, but it's not exactly linear, right? So after creating the data, let's plot y versus x. So we use the dots to represent the plots. Right? You can use circle, can use x. It will just show differently. For example, if we use x, this will be x. All of the points will be x, and we set the color to be blue. B means blue here. And we plot out the x label, plot out the y label. We can also set the font size of this letters x and y. We didn't do that. If you think it's too small, you can definitely set the font size. So this data look linear, and now let's compute the best linear line that passes through the data points. Right. That means we want the squared sum of the residues to be the smallest, right? That's our least square criteria. So we want to find the optimal linear line. Let's first use the formula we had here. I use the normal equation to do this. We first need to create the x matrix. Remember, the x matrix is m by m plus 1 matrix. So here the capital N is 100 because we generate 100 data points. So capital N is 100. The lowercase n is 1, right? Since we only have one feature, which is a single x. So originally, we only have one feature, and we have, remember, for the x matrix, we have additional column of ones. So it's 1 plus 1, that's 2. So it will be a 100 times 2. 100 by 2, that's the size of capital X. And here we create the X matrix. What we do is we do a column stack of 100 ones and X. Right? NumPy.ones, 100 give you 100 ones as a 1D array. X is a 1D array. So we want to stack this to 1D array vertically. We use C underline. So X will be, this is a 100 by 2 matrix. First column will be ones. Second column will be the X values. Right, that's the X required here. And we already have Y. Y is simply the Y here. We don't need to change anything about it. So we have the capital X matrix, we have the Y vector, then we can simply evaluate the normal equation here. So what we need to do is X transpose times X. And remember in Python, what we do for matrix multiplication is NumPy dots, that's the matrix multiplication, and not a star. Right? NumPy dot is matrix multiplication. So we first multiply X transpose and X. X dot T means the transpose of X. And we need to find the inverse of the products. To do the inverse, we need to use the built-in function numpy.linearalgebra.inverse.inv. Right? This gives you the inverse of a matrix. Right? So the first part here basically gives you the first quantity here. Right? Then you want to multiply the result by X transpose. What you can do is do a dots X transpose. That means you multiply X transpose. And you want to multiply, after that, you want to multiply Y, then do a dot Y. Okay, so this will give you beta hats. So we store this number in beta, this is vectors in beta hats. When we print out beta hats, it gives us 4.22, 2.82. Right, does it make sense? Look at what the exact value should be. Right, the exact value should be 4 and 3. Right, for this line, this linear line is not too far away. It can't be the exact 4 and 3 because you have some noise here. Right? Unless you can denoise the data exactly, right? Otherwise, you will not get exact 4 and 3. But this is pretty good. It's very close to the true linear relationship. Right? So this means the normal equation actually works. And do we have to do this, right? Do we have to do this? We have to build the X matrix. We have to find the Y and use the normal equation to evaluate this long dot product to get beta hats. Or actually, it's not necessary, right? Although it's not very cumbersome, but we have some built-in function to do this. So before we talk about how to use the scikit-learn package to do that, after we have this linear regression function, then we can actually make some predictions. Right? For example, let's predict, use the linear function to make predictions for 2 additional or 2 new X values. One is 0. 0 is here, it happens here. The other one is 2. Right? 2 is here. We want to make the prediction for X equal to 0 and X equal to 2. So we put 0 and 2 in the 1D array. And they are the new values. And then we want to create the X matrix corresponding to the X values. Okay, so right now it's 0 and 2. We want to make it in this form. 1, 1, 0, and 2. And that means we want to add an additional column of 1s. And why we'll do that? Remember, because for each f of x, right, that's actually beta 0 plus beta 1x. Right, so you have 1 times beta 0, that will give you beta 0. So you need to have a 1 here. Right, x is 0, 0 times beta 1 is here. So we want to do a dot product of beta hats and this x value. But beta hat has 2 numbers. X value for here, just 1 number, 0 or 2. Right, so you need to add a 1 here. Right, so beta 0 multiplied by 1 give you beta 0, beta naught. So we want to add an additional column for 1. That's the same as when we create the X matrix. Right, so we create a column of 1s with 2 numbers, and we do a column stack with the new data. So we have a matrix like this. This will be X new. So I have this matrix here, and to do the prediction, you simply do this matrix times the beta hats. Beta 0, beta 1. Let's call this beta 0 hat, beta 1 hats. So X new times beta 0, beta 1 hats, we can evaluate this, right? This is a 2 by 2 matrix times a 2 by 1 column vector. So the result will be a 2 by 1 column vector. Right? The first entry will be 1 times beta 0 hat plus 0 times beta 1 hat. Beta 0 hat plus 0 times beta 1 hat. Second number will be 1 times beta 0 hat plus 2 times beta 1 hat. Right, so this will be the prediction corresponding to the X value 0. This will be the prediction corresponding to the X value 2. right? So the result will be the two predictions. So we only need to multiply x new and the beta hat vector. So what we do is do numpy dot x new and the beta hats. This gives us a 2x1 vector, right? It's a 1D vector with two values. So we call this y predict, right? The predicted y values. And we print this out. The first value will be the predicted value corresponding to 0. Second value will be the predicted one corresponding to x equal to 2. Based on these two predictions, right, one is here, the other one is here, then we can actually plot out this linear line because 2 points decide a linear line, right? Then we can simply plot x new and y predict. And we set the color to R. This gives us this red line here. That's the regression line. And we plot this data points again using a scatter plot to set this so you get the data point. Right? You can, I use the circle here, right? You can also use dots, right? Make it smaller. Either is okay. We get the scattered data points, and the second one, we get the regression line. Set label X, set the label Y, print out the legend. So training data and regression. So you can see just visually, this linear line fits the data pretty well. All right, so we can use the linear line to make predictions for new data points for new X. All right, so everything we have done here is to use the normal equation to find the linear line. You can actually save a lot of troubles by just to use the linear model in scikit-learn, in the scikit-learn package. Well, we have seen something similar to this in the first lecture notes. Where first imports sklearn .linear model, where we have done that at the beginning, and we call this linear regression function. Another way to do this is you can, from the sklearn.linear model, import linear regression. Then you can just directly call linear regression without using sklearn.linear underline model dots. Simply call linear regression. Either way is okay. If you want to make it shorter, you can do that. So first to build the model, this is an empty model, right? We haven't trained it yet. And after that, we can train the model. So to train the model, we call this fits, right? You can use any name for LIN underline REG, or you can call it just a model as we did before, or you can call it A, right? You can call it anything. Right here, we just try to mean this is a linear model. So we call it LIN underline rec. And we do the fits for the fitting for the training. Remember, your X data has to be a 2D matrix. Right here, your X is simply a 1D vector to make it 2D because we only have one feature here, right? So originally that's a 1D vector, right? To make it 100 by 1 2D NumPy array, right, we can simply call this C underline. This make it a 2D array with just one column. And Y is a 1D array, that's fine. And the training is done. After the training is done, we can print out the intercepts underline. That's beta 0. Then we print out the coefficients. The coefficients are all the coefficients other than beta 0. So in this case, there's only one. That's beta 1. And print it out, it shows us 4.22 and 2.82. And let's see whether they're the same as what we did before, what we got before. Right? They're the same thing. Not here, right? Not here. Yeah, here. They're the same thing. Right? Everything is the same. And then we can do some prediction. Then we use the model, predicts here X new. Remember, X new has to be a 2D array. Right? Originally, X new is simply a 1D array with two numbers 0 and 1. And make it 2D, that's the same. We use C underline, numpy.c underline. So now it becomes a 2D array with only one column, a 2D matrix with one column. So, well, after we call this predicts, we should get two values. One is the predicted value corresponding to 0. The other one is corresponding to 2. and we'll print out these two values to give us 4.22 and 9.87. It's the same as what we got before. Right, this is the way to use the linear regression in scikit-learn to do linear regression. Right, this is the second time we use this. Right, let's look at another example here. This example used the data stored in LEC2, that's lecture 2, example 2.txt. Right, you can download this data from the files in Canvas. And to explain this data a little bit, so the first, if you look at the data, first we can call the numpy.load.txt. So it can load txt file into a numpy array. We call this numpy array data. And if you check the data, there are 3 columns. The first columns are all ones, right? Because it's the same as what we did before for that capital X matrix. The first column are all ones. The second column are the feature X. And the third column, they're actually the Y's. Right, so here we only need the first column, the second column. They are the features, right? So we extract the second column. Right, here we add a brackets, right? It's important to understand what's the difference between using the brackets and without using the bracket. If we do this, X equal to data one. So we extract the second column from this numpy array, but we only get a 1D array. If we add this brackets, we still extract the second column, but at the end we get a 2D array. But that's the only difference. Since we're going to use the 2D array later for the linear regression model, let's put this in 2D array for now. Right? Otherwise, you can also just do this without using the bracket, but later you need to use numpy.c underline to convert this to a 2D array. And to save that trouble for now, here actually we just directly get a 2D array. It's the second column. That's going to be the feature of the problem, the feature vector. And Y is simply the third column, so it's data 2, right? That's the extraction of the third column. And we'll make a plot and see what the data look like, X and Y. We use dots to do the scatter plot, and that's pretty much linear, right? So then we can do a linear model. Same thing, we construct an empty linear model here. This is actually building an object from linear regression class. And we train the linear model, X and Y, it's obtained here. Just use them. After we've trained the model, let's look at the parameters. The parameters, first the intercept, and then beta 1. This is beta 0, this is beta 1. Right? That means the slope is 1.7, the intercept is about 3.0. And let's do a plot of the linear line. What we do here is we create 2 values. One is 0, that's here. The other one is 1. So we find what's the predicted value corresponding to 0 and predicted value corresponding to Y. Then we just connect these 2 points to it gives us the linear line. Right? That's the same as what we were doing before. So we create 2 new X points, 0 and 1. Then we do a predict. First, convert this to a 2D arrays and call predicts. It gives us the predicted values corresponding to 0 and 1. Then we do a plot to connect these 2 points. It gives us this regression line, and we set to be red. All right, so it's a very simple problem. This is like a revisit about how to do linear regression using scikit-learn. All right, let's move on to the second section. The second section is about polynomial regression. Right? Suppose if you check the data, right? The data may look nonlinear than what you can do. Right? Then we can do something called polynomial regression. That means you can add, for example, square term or cubic term or higher order degree polynomial terms to your regression. Right? The polynomial regression is actually linear regression. It's just fits in the term a generalized linear regression. Right? It's still a linear regression. Right, but here we emphasize we add higher degree terms about the feature, about X, into your model. So we look at an example that not much different. Here we create some data points that look it also actually nonlinear, right? So for this particular example here, we create 100 data points, and we first create X data. So again, rand gives you random, uniform random number between 0 and 1. So here we generate 100 uniform random numbers between 0 and 1. We multiply it by 6. So 6 times this 100 numbers, it gives you 100 uniform random numbers between 0 and 6. Minus 3, resulting 100 uniform random numbers between -3 and 3. Right? So here, this line actually generates 100 uniform random numbers between -3 and 3. Then the original function is 1/2 x squared plus x plus 2. That's the true function. And we add some Gaussian noise. Right? This is a standard normal variable. We add some Gaussian noise and plot the data x and y. We can see this is data. Right? It's a perfectly quadratic. And now we use some built-in function in scikit-learn to do polynomial regression. Right? Here, what we want to do is originally we only have the feature x, right? Just a column. This is a column data. That means the 100 numbers between -3 and 3. Right? This is a column data. And also here suppose we want to add the x squared as a new feature. Right? What you can do is simply add a column x double star squared and do a column stack of the data. Then you get this this new second column here, x squared. Right? But in general, suppose you are including maybe power to the power of 100, and what you do, you have to do it's first the x double star squared, x double star 2, x double star 3, and 2x double star 100. And suppose you have multiple features, for example, x and y. You also need to include x, for example, to the 40th, y to the 60th. There are a lot of such terms, x to the 30th, y to the 70th, too many terms. You can't just do it by hand. Right? So to include polynomial terms, we can actually use a built-in class in scikit-learn that's polynomial features. Well, we imported polynomial features at the beginning of this lecture notes. Here, the most commonly used arguments are two. One is the degree. Right here, it tells you what's the degree of your polynomial, the degree of your polynomial function. Here, we're considering degree up to 2. Right? Since here we know it's a quadratic function, right? So we just specify the degree to be 2. That means we're only looking at quadratic functions. Right? If you set degree to be 3, then it will look at x squared, and x to the 3rd, right? Cubic function. Include bias equal to false. That means after you generate the features, it doesn't give you a column of ones. Right? If you set it to be true, it will give you a column of ones. You don't need this column of ones. You only need x and x squared. right? Then you just set it to false. All right, so we first create this polynomial features objects. We call this poly. And then we make it 2D to do a transform. That means at the higher degree, it will work on 2D data. So we first convert X, which is 1D data, to 2D. So we call this X matrix. Right? Use C underline. Right? So make it a 1D array to 2D array. Right? The value doesn't change, just the shape changed from 1D to 2D. So the X will be a 100 by 1 2D array. Right? X is given here is 100 data points. So it's X, size of X is 100 by 1. Right? So it's basically this data here. Right? 100 by 1. And you use fit transform, poly.fit transform X. What it does, it will add the additional features. In this case, there's only one column of additional features. That's X squared. Right? Suppose you set degree to be 3, then it will add X squared and X to the third. Add 2 more columns. So what X now? It becomes, the shape becomes 100 by 2. That's just this one. This is your X right now. First column is the original X value. Second column is X squared. You don't need to manually do X double star 2 to add this X squared. It would do it for you automatically. Print out the shape. We can see it's 100 by 2. Right, we look at the first column. What the first row of X is 1.74, 3.02. 1.74 is the first data point you created here. And the second number, you can check, that's the first number squared. Right, for each row, the second number will be the first number squared. All right, now we can use the linear regression object class here. First, create linear regression objects. And now we can do the fit xy. X here contains 2 columns, X and X squared, 2 features now. And we print out the intercept and the coefficient. Intercept a scalar. Coefficient now, this is beta 0. We have 2 coefficients, beta 1 and the beta 2, because we're looking at a quadratic function. So we have beta 0, beta 1, beta 2. Right, so this means the model is 2.0834 plus 0.9883x, that's a linear term, plus 0.4890x squared, that's the quadratic term. Right, so for quadratic, so for polynomial regression, it's still a linear regression. It's just you need to add more features. You need to add the higher order degree features. Right, to do that, use the polynomial features. It can add all these features, higher degree features automatically. So now we have the quadratic model. We want to visualize whether the model fits the data well. Right, so what we can do here is we first plot the data point. That's the blue one, the data points. So this is the first line. This is a scatter plot of the data points. And then we create 100 data points for plotting. Right? The second line is some new X data points. They are simply for plotting. You can use the original 100 one, right? That's fine. Let's use some new data points for plotting. It's between actually 3 and 3 and 100. Right? Link space, that's a linear space. That means we're creating a 1D array of 100 points. These 100 points are uniformly or equidistantly distributed between actually 3 and 3. And this is a 1D array, right? To use it for predicting, we still need to add the quadratic term corresponding to the new X values. And then we call it the poly-fit transform. Okay, that means we add the second column corresponding to the new data point. And now it becomes 2 features. One is X values and then X squared, similarly to what we have just done, right? Add a new column. Here, the fit transform takes argument, takes inputs, takes a 2D array as input. So you first need to use C underline to convert it to a 2D array, then call the fit transform, you will get X new. The X new is again 100 by 2. The shape is 100 by 2. And then you can you can make predictions for this new data point. So you can use linear regression dot predict X new. This will predict the new predicted Y values corresponding to the new X values. And set the color to be red. Label it as regression. You will get this red line here. You can see the red line, the regression curve fits, the regression function fits the data pretty well. Right? So the polynomial feature class is really, really useful here. Right? This is another example here. Suppose you have two features, originally you have two features, x1 and x2. And if you set degree to be 3, that means, let's go back to here, right? If you set degree to be 3, then how many features will there be? Originally, you only have x1, that's the first column, x2, second column. And the polynomial features class, after do the fit transform, if you set the degree to be 3, it will add 1, 2, 3, 4, 5, 6, 7 new features. Right? For example, this will be x1 squared, that's the third column, x1 cubed, right? And x2 squared, x2 cubed, x1, x2, x1 squared, x2, x1, x2 squared. Look at the total degree. Each of the term has a total degree of 3 or less. Right? This is degree 3, degree 3, degree 2, degree 3, degree 2, 3, 2. It doesn't exceed 3. It contains all of the term, the combination of the features that has degree less than or equal to 3. So you can see the poly features does it really simple. Otherwise, if you want to do this manually, you have to x1 double star 2, x1 double star 3, then you need to do x2 double star 2, right? And then you need to column stack them. Right? This is really, really cumbersome. So that's why we use the poly features. All right, so this is an example of doing polynomial regression. All right, so the next topic is very important. We'll talk about some regularized linear models. Right, you can also see some call this shrinkage methods or shrinkage models. Right, that means so yeah, to talk about why we want to do this, we need the concept of overfitting. Right, so overfitting is a very common problem that you will see in machine learning. Right? That means you have some data, training data, then you want to build a model based on the training data. Right? Then what's your purpose? Your purpose is you want to predict well, make good predictions for new data, make accurate prediction for new data. Right? But sometimes people tend to overfitting the training data. That means it uses some more complex models to represent the training data. Remember what we did before for this data. This is the data we used before, right? This is the life satisfaction model versus GDP per capita. Remember we used just linear line to represent the data before. Right? Suppose you want to use a more complex model. In this case, we use a higher degree polynomial to model the data. And you could get something like this. Right? You can see this compared to the linear model, this model fits the data much better. You can see a lot of points are on this data. And for this, this data points that are far away from the majority, they're also located on the regression curve. So this means for this training data, it definitely works well. But can it generalize well to new data? The answer in general will be no. That means you are doing too much work. You are trying try too hard to improve your model such that your model works well on the training data. But if you do this, it tends to work worse for the new data because you're making this too complex, so that it doesn't generalize well. Right? This is called overfitting. Right? This is an example of doing overfitting. Instead of using a very easy model or just a model with a lower number of features, here you are using a lot of features. It's a much more complex model. You're using a high degree. For example, degree up to 20, that means you're using 20 features. A more complex model. Try to fit the training data well. That's okay if you only look at the training data, right? It does work better compared to the just the linear line, but it will not generalize well, right? So this is called overfitting, and it happens. It happens when you're using very complex models relative to the amount and noisiness of the training data. Right. So how to understand this? For example, if you're looking at only this data, it's clear everything here. Right? If you're only looking at these data points given, right? So maybe this is the model that you want. Right? But actually, if you had more data points, right? Maybe the data points are given here. Right? Let's just add maybe 10 times more of the data. For example, we can collect more data. I'll put all of the data, newly collected data here. Right? Is this still a good model? Maybe not. Right? Let's put the data here. Is this higher degree polynomial still a good model? Probably not. Right? And what is better? That we just simply, for example, we just use a linear line that could fit much better than this polynomial, the higher degree polynomial. Right? That means relative to the amount of data, your model is too complex. And also, sometimes the data is too noisy. Right? For example, look at this data here. They can be outliers. Right? It can be because there's too much noise related to this data. Right? So, for example, suppose you also have the data here. Right? So maybe the data, the actual data is close to here, but since there are too much noise, then the data is located here. So if the data is here, then maybe the linear model works better, right? But since there's too much noise and the data is here, then that makes you think the linear model doesn't work well for this data point, and you want to use a higher degree polynomial to include this data on the regression curve. Right? So this is why the overfitting happens. And what's the possible solutions corresponding to the reason of why this happens? There are 3 ways to overcome the overfitting problem. First one is use a simpler model. A simpler model means a model with fewer parameters, with fewer features. For example, you just use a lower degree polynomial compared to a higher degree polynomial. Second is gather more data point for training. If you have more data points, maybe the picture is clearer, and you will get a better model. And the more training data you have, the less possible that you will get an overfitting model, or reduce the noise in the training data. Right? Just as we mentioned, the noise can affect where the data is, and it can affect your model. Right, so how can we how can we overcome this problem if we're using a linear regression? And also, for example, we're not just doing a linear regression, we're doing a polynomial regression, right? Because in general, in most cases, right, the model will not be purely linear, right? It has some nonlinearity inside the data. Then you're going to use a polynomial feature, so polynomial regression. If you're using polynomial regression, then you will have a lot of more features compared to just linear regression. Right? In this case, how can you solve the problem? You're making the model more complex by using polynomial terms. Right? In this case, it means it's possible that overfitting happens, but how can you control the overfitting? Right, that's our goal next. So we'll introduce some methods. They're called regularization methods, right? Again, we also call it shrinkage methods. We talk about this when we talk about here, right? Regularized linear models. We call it regularization or shrinkage. So all of the methods we introduced here, they are trying to lower the magnitude of the coefficients or parameters, beta i's. Right? The idea here is if we're using more features, the coefficients or parameter values will also get large significantly. Right? The size of the coefficients increases with the size of the features. So eventually you can see if you include more features, and you will find that the coefficients get larger, or get really large. And that gives you the overfitting problem. So the regularization and the shrinkage method try to lower the magnitude of the coefficients, right, just to overcome the overfitting problem. So that's also why it's called shrinkage, right? First, the size of the coefficients gets smaller, and also you can see some of the parameters are fixed to be 0, right? So that means you can ignore some of the features so that you have a smaller collection of the features. This is also called feature selection. And we'll talk a little bit more when we talk about the detailed methods for regularization. So there are 3 methods we're going to talk about: ridge regression, lasso regression, and the elastic nets. Right? They have something in common, and they're all used for linear regression. So for ridge regression, what's the difference? Remember, for linear regression, we're trying to minimize MSE or RSS, right? They're the same thing. Or suppose we're trying to minimize MSE. Here, for ridge regression, not only minimizing the mean square error, I'm minimizing the mean square error plus an additional term, right? The additional term is actually alpha times 1/2. This is alpha over 2 times the squared sum of the beta I squared. Here I starts from 1. It doesn't include the intercept term. And you can also rewrite this. This term is what? This term is actually the beta vector 2 norm squared. It's actually the L2 norm squared of beta. So you are actually adding a second term, which is alpha over 2 times the L2 norm squared of beta. So you can think about what does this term do? This term actually tries to control the size of beta. You're trying to minimize the whole thing, right? The second term definitely cannot be too large. Right? If your beta, your coefficients are large, the second term will be large. Since we're trying to minimize this, the cases where beta i's are large will be excluded. Right? That will not be the minimizer for your J beta here. So it excludes those cases where beta I will be large. Right? So in other words, that means in this way we can lower the magnitude of the coefficients. Right, so this is one way to do that. We call it ridge regression. It also has a closed form solution. This is very similar to the normal equation. Right? The only difference is here. It's alpha times A. Right? We talk about what A is. All right, the second way to do this is called a lasso regression. Right? So ridge regression, another way is called lasso regression. Another way to call ridge regression is Tikhonov regularization. Right? It's just a different name. For lasso regression, instead of using the L2 norm, we're using the L1 norm. So we add alpha times the L1 norm. So this is alpha times the L1 norm of the beta vector. Right? The sum of the absolute value of beta. Still beta, the beta here doesn't include beta 0. All right, so again here, the second term also controls the size of beta I. For those large beta i's, the second term will be large. Right here, we're trying to minimize this j beta. So if the second term is large, it will not be the solution of the minimization problem. Right, so it tries to find those solutions with the smaller beta i's. So in other words, it also lowers the magnitudes of beta i's. Very similar to ridge regression here. Right? One is the L2 norm, add a L2 norm. Another one is add a L1 norm. Right? Also, in the first case, you can see if alpha is equal to 0, then what happens? That means it's reduced to the original linear regression problem. Right? Same thing here. If alpha is equal to 0, it's reduced to the linear regression problem. And how to pick alpha, right? There are some ways to pick alpha. In general, you don't know what alpha you should do or what alpha you should use, right, to make it a better method, right? Usually what people do something called grid search. That means we use a bunch of alpha, for example, 100 alpha values between a very small number, like 1 e minus 10, to 1. Right, we pick 100 numbers between those in this range, and we see which one is better. But in general, a priori, you don't know what alpha value should be taken. All right, so this is the first two methods. The third method, elastic net, is a combination of the first two. That means we have a term related to, we add a term related to the L2 norm. We also have a term that's related to the L1 norm. For L2 norm, that's the ridge regression. L1 norm is the lasso regression. Right here, we use coefficients R and 1 minus R over 2 to control how much L1 norm you want to add, how much L2 norm you want to add. Right? You can think about two extreme cases. Suppose R is equal to 1. So what happens? This term goes away. This becomes alpha L1 norm. So it's reduced to lasso regression. Another case is if R is equal to 0, this term goes to 0, this term becomes 1/2. So it's reduced to the ridge regression. Right? Elastic net is kind of, there's some elasticity that you can control so that you can move it towards ridge regression. You can also move it towards lasso regression. So it's a combination of the two, right? All right, so, and we'll not go into the detail of the three methods, but what you should understand what we're doing here, right? We're, based on the linear regression, the least square solution, we're adding some term in the cost function that controls the size of the coefficients. And elastic net is a combination of the first two regularization methods. Right, and actually, elastic net, ridge regression, lasso regression, they are also very active research topics right now. But some general usage or some general idea about linear regression, there are some hints here. Right? When you think about using linear regression, when should you use original linear regression? When should you use ridge regression? When should you use lasso? When should you use elastic net? Right? There's some general idea, right? So it's all case by case, but there's some general idea. The first thing is for linear regression, you should, most of the time, you should use some regularization. Right, because you want to avoid overfitting. You should use one of the forms or other more sophisticated regularization methods. Right, but what's the characteristics related to the three methods? Right? So The idea here is the lasso regression tends to put the coefficients to 0. Right? So lasso regression is good for a large number of features and the feature selection. It tends to estimate the coefficients such that the coefficients are 0. Right? In other words, it tries to give you estimates such that the estimates of the coefficients are 0. So it's very good for feature selection. Suppose you have 100 features, right? You want to know which features are more related to your function output or target value. It may be only related to a few features. You want to know what are those features, right? In this case, you can use a lasso regression because it tends to give you to select the features that are more important. And what's the cost of doing a feature selection? If you look at the performance, right, the performance here may be worse. May be worse compared to the ridge regression. The ridge regression, it doesn't fix the coefficients of a lot of features to be 0. Right? It tends to give you small coefficients, but not 0 coefficients. Right? So in other words, it doesn't do feature selection automatically, but if you look at the performance of ridge regression, it can be better than lasso regression. So by performance, it means, for example, the residual sum of squares, right? RSS of the ridge regression may be smaller than RSS related to the lasso regression. So this means it's a better fit, right? But it doesn't give you feature selection, right? But if you want feature selection, you don't care about the additional or the smaller or the better performance of ridge regression or the better fitting of the model, or you can use lasso regression. So it depends on which one you care about. If you want a better fitting, you use ridge regression. You want to do a feature selection. You want to find a sparse model, which means a lot of the coefficients are 0. There's only a few non-zero coefficients. So it's a sparse model. If you want a sparse model, you do a lasso regression. But if you want to combine both, you don't want your model performance to be bad. You also want to kind of do a feature selection. You just do elastic nets, right? It combines both of the advantages, and remember, it also combines both of the disadvantages. So this is a middle ground between the two. Right? So it's important to understand the advantages and disadvantages of lasso and the ridge regression. Right, so we have some additional exercises asking about disadvantages, disadvantages of these methods. All right, so the last thing is, since we have known the theories related to the 3 regularization methods, and let's see a detailed example of using the regularized linear regression, how to use scikit-learn to perform the regularized linear regression, and what we can conclude from the different methods. Right, so here we do a synthetic example here. We first create some X data. Right, here, what we're doing here, this gives us a list. For I in range 60 to 304, this means we're generating numbers from 60 to 300 with the step size of 4. So that means 60, 64, 68, 72, until 300. Those numbers are divided, multiply these numbers by pi and divided by 180. Right, so this is a list. This is a list of numbers. Right, so you're actually getting a list of numbers between 60 times pi divided by 180, so that's 1/3 pi over 3. And the last number will be 300. 300 should be included. May or may not include it, right? You don't care about that. It's around 300 pi over 180. Right. This is a list of this of the numbers, and we put it into convert it into a NumPy array. Okay, so the next number is actually 64 pi over 180, right, and so on. We create this number. So these are actually 60 degrees to 300 degrees. They're converted to radians. Right? These are the radian. And we're going to use for sine function. So we're going to create a sine function based on these x values. And we add some normal random variables. Here, its mean is 0. Its standard deviation is 0.15. And we add the Gaussian noises, the same number. Right? We have the same number of Gaussian noises as the number of x values. And we make a plot. Right? This is the sine function between pi over 3 and 300 pi over 180, and with some noises added. And the next thing we want to do is let's use polynomial, or let's use linear regression or polynomial regression to approximate or to find a regression for these data points. Here we use polynomial regression. Let's consider polynomial regression with powers of x from 1 to 15. 1 is just the regular linear regression. And starting from 2 to 15, they're polynomial regression. Right, so again, we're going to use the polynomial features. So here we set degree to be 15. Again, we set include bias to be false. We don't need that column of ones. So get the poly objects, right? Based on the poly objects, we can do a fit transform. So we get the x data here. The x data now becomes a, yeah, we don't know how many data are there, right? Let's just say it's n by 15. Right, n by 15 here we have x squared. X is the first column, x squared second column, up until x to the power of 15. So we have 15 columns. We print out the first row. We can see first number is 1.04. 1.09 should be 1.04 squared. 1.14 should be 1.04 cubed to the power of 4, and so on. 1.9972 should be the number 1.04 raised to the power of 15. And let's look at a few cases. Right? There are too many, when we make plots, there are too many cases. Let's just look at a few cases corresponding to the power of 1, 3, 6, 9, 12, and 15. Right? Let's see how they perform. Right? So here we set one of the parameters related to RC params, the figure.fig size. That means we want to make you can see there are some subplots here. So we want to see this clearly. We want to make these plots bigger. So it sets the figure size to be 12 and 10, right? So we have a bigger canvas here. And then we'll do some subplots. Right here we specify which degree we want to look at. We want to look at degree 1, 3, 6, 9, 12, 15. So we put them in the list. And then we set up the subplot positions, right? So there are, you can look at the subplot here, 2 rows, 3 columns for the subplots, right? So we want to set up a dictionary here. That means for degree 1, it corresponds to 2, 3, 1. 2, 3 means 2 rows, 3 columns, the first plots. That will be this position here for the subplots. Second degree is 3, so 3 corresponds to 2, 3, 2. 2 rows, 3 columns, the second position here. So we'll plot the power 3 at this position here. Similar for 2, 3, 3, that's the position here. 2, 3, 4, here, 2, 3, 5, 2, 3, 6, right? This is what it does. And now we'll do a for loop to make the plot. To make the plot, that means we want to plot do the scatter plots of the data points. Then we plot the regression curve corresponding to different powers. Right, so we do a for loop in the range of length of degree. Length of degree is 1, 2, 3, 4, 5, 6. Length of degree is 6. Right, so I will be taken as 0, 1, 2, 3, 4, 5. Right, 6 values. For example, when I is 0, right, then we'll do a subplot dict degree 0. Degree 0 is what? Degree 0 is 1. So degree I will be 1. Subplot dictionary 1, that means it try to find what's corresponding to 1. Corresponding to 1, that's 2, 3, 1. So everything in here will be 2, 3, 1. So what it does in the first iteration is plot subplot 2, 3, 1. So to make subplot here, we do a tight layout so that you don't have overlapping of the titles, the axis. That's for tight layout. You can check what you see if you don't do tight layout. It can happen that overlapping of the axis will happen. All right, so for the first subplot here, what we do is we first fit the model. Right, we use sklearn.linear model, linear regression, normalize equal to true. Right, so before we didn't set this to be true. Right, normalize equal to true. Actually, you can see what it does. It just to try to normalize the data. Right, first subtract the mean of the data and divide the data by the 2 norm. Right, so just try to do some like centralize the data. Right, so it doesn't. After do the normalization, it's just to. For example, it's close to a certain range. It's not scattered all over. And this is a good practice actually to set normalize to be true when we do linear regression. And same thing for the other regularized linear regression. It just kind of improved the accuracy of the linear regression. And we set normalize to be true, and we get the linear model, and we train the model. Right? So we train the model. Here, remember, I in the first iteration, that's 0. So degree 0, that's the first one. It's 1. So 0 to 1 is just 0. So we're just using the first column of x. The first column of x, that means we only look at the linear term. Right? That's what we want, linear term. And we fit x and y. After fit x and y, we predict for this x. And that means for each of these data points, we look at what's their predictions on the line. And after we get the prediction, then plot x and y predict. That will give you the linear line in the first case. Right? Plot x, y dots, that will give you scattered points. This is the same for all of the subplots. And we plot the title, plot for power. Right? This is the formatting of the string formatting. Right? You're trying to plot, D means an integer. Well, what's the value of the integer? The value of the integer will be degree I. Degree I in this case is 1. So when it printed out, it will replace this part by the value of degree 0 in this case, that's 1. So replace this part by 1, it's plot for power 1 is printed out. So that's the first iteration. Look at the second iteration. Second iteration, I will be 1. And we look at degree 1. Degree 1 is 3. Subplot dic 3. 3 corresponds to 2, 3, 2. So this part means 2, 3, 2. So that's the second position of the subplot. So it will make a subplot in the second position. And we do the tight layout. We do the create a model, linear model. Then we fit x 0 to 3. 0 to 3 means 0, 1, and 2. So it uses the first column, second column, and third column of the input data. Right? That means you are including the linear term, quadratic term, and cubic term. Right? That's what power 3 means. And use these 3 columns to fit the data, make a prediction for the x data. and make a plot, you will see this blue curve. This blue curve corresponds to the cubic function that's fitted to this, this data. And for the rest of the plots, they're similar. Right, this is the degree 6 function, degree 9 polynomial, degree 12 polynomial, degree 15 polynomial. So you can see there are a lot of oscillation corresponds to higher degree polynomials. And this is a sign of overfitting. You can see this is a sign of overfitting here. This is a, you don't see the overfitting here because you can see it's a smooth and it's since it's power 3, right, only 3 features. It's a simple model. Then here you can see it gets really complicated, a lot of oscillation here. And also what we can do is we'll print out the coefficients corresponding to models. One is a relatively simple model, degree 3. The other one is degree 15. We'll look at the coefficients of the 2 models. So first for power 3, let's train the model again, which we train the model, use the first 3 columns of x, right? Degree 1 here, that's 3, so it's 0, 1, 2. So use the first 3 columns of x, train the model, then you print out the coefficients, right? You can see the coefficients are given here. Right, sorry, coefficients are given here, right? The size is not very large, but if you're using a power 15, right here, degree 5 is the last value here, that's 15. You're using all of the columns of x. After you train the model, you print out the coefficients, you can see the size of the coefficients are really large. To the power of 5, to the power of 5, to the power of 5, and so on. Right. And you can see, as I mentioned, if you're using a very complex model, if you're using more features, the size, the magnitude of the coefficients will also increase. And that actually causes overfitting. So you can see that's why what we call it shrinkage methods or regularization methods. We want to control the size, the magnitude of the coefficients. All right, so then we're going to use the regularized methods. Right? For example, let's use the ridge regression first. And let's see what we can get. So for ridge regression, one of the problem is, first, we don't need to consider different powers. We'll use all of the 15 powers. We don't worry too much about overfitting by using more complex models because the regularization will take care of the size of the coefficients. But we need to take care of the different values of alphas. So here we use a bunch of alpha, and let's see which one could serve as a good model. And let's use 6 different values. Again, we set the size of the plots to be bigger. Degree is 15. We use all of the 15 columns of x. And for subplots, different positions, 2 columns, 2 rows, 3 columns, 1, 2, 3, 2, 2, 3, 3, 2, 3, 4, 2, 3, 5, 2, 3, 6. That's the positions of the subplots. All right, so we'll do a for loop so that we can use all of the alphas. For each iteration, we're using 1 alpha. Right, for the first iteration, we're plotting here. We do a tight layout to avoid overfitting. Then we fit the model using ridge. For ridge regression, it's very similar to linear regression. Just replace linear regression by ridge. Also need to set what's the alpha value you use. Here we use the first alpha value, 1e minus 15 in the first iteration. Still set normalized to be true. And after you build the model, this empty model, and you do a fit x and y, you're using all of the columns. So just to use x here. Then you predict, make predictions for your x. And all this y prediction, you can make a plots x and y prediction. So it will give you this blue line, blue curve here. That means you are using all of the 15 features, right? That means x cubed, x squared, x cubed into x to the power 15, and you use the ridge regression where alpha is taken as 1e minus 15, 10 to the power of 15. For the second iteration, you will use alpha as 10 to the power of negative 10. For this case, that's 10 to the power of negative 4, 10 to the power of negative 3, 10 to the power of negative 2, and the last one, alpha is equal to 5, right? So here we're using all of the 15 features and with different alpha. And if you remember, when alpha, for ridge regression, when alpha is close to 0, and you can see the regularization is basically doesn't exist, right? It's just reduced to a linear regression. So you can see when we use a very small alpha here, you can see the overfitting is still there because you can see it's not very, there's a lot of oscillation. But when we increase the size of alpha, for example, when we increase it into 0.001, and actually when we increase to 1e negative 4, it becomes very smooth, right? So although we're using all 15 features, but the regularization just reduces the effect of overfitting, right? If we use a very large alpha 5, right, that's just, it doesn't give us very good result because it tries to, right, the second term of in the cost function tries to dominate, right? So eventually it will give us a flat line, right? So based on this, we can use either this 1e negative 4, 1e negative 3, or 1e negative 2, right? So for example, let's use 1e negative 3 and print out the coefficients and see what we get, right? So we construct the model again, use ridge regression, set alpha to be 0.001, and we do a fits. Right here we can just use x, or we can use 0 to 15, right? They are the same thing. You can just simply use s. We do a fits, then we look at the coefficient, print out the coefficients, the size of the coefficient, although we're using 15 features, but the size is really small. All of the sizes are very small. All right, so the last plot, you can see this is something called underfitting. Right? That means you are using a oversimplified model to represent your data or to model your data. So it's kind of underfitting. Right? Underfitting is basically the upside of overfitting. Your model is too simple. It doesn't learn your model. It doesn't learn the data well. Okay, so this is a case of underfitting because you're trying to suppress the size of the magnitude of the coefficients too much, right? Maybe many of the coefficients become 0, right? For this case, so your model is too much simplified. Right. Similarly, let's look at the lasso regression. Everything is still the same. We use a 6 alpha here, and the only difference here is we use lasso instead of reach. Right? Everything else is still the same. Then we look at the alpha values, the plots corresponding to different alpha values. So 1e minus 10, 1e minus 5, or 1e minus 4, 1e minus 3, 1e minus 2, and 1. All right, again, this happened. This is a underfitting. You have, since the alpha is too large, all of the coefficients become 0. Then the regression curve is a straight line, horizontal straight line. And for 0.01, right, this already become too large, right? Such that it's a straight line. And what could be a good one? For example, 1e minus 1e minus 3 in this case is pretty good. You don't see overfitting, you don't see underfitting in this case. And let's just use this as example. We train this model using this alpha again, do a fit, and we print out the coefficients. And you can see coefficients not very large. And what's evident here, what's more important here, we can see a lot of 0 coefficients here. And here the 0 coefficients, that's different from the ridge regression we just looked at. For the ridge regression here, you can see although the size, the magnitudes of the coefficients are controlled, but you don't see any 0 here. Right? But for the lasso regression, not only the sizes of the coefficients are controlled, but you can see there are a lot of zeros. Right, that's just as we mentioned before, lasso is good for feature selection. It tends to set a lot of coefficients to be 0, right? But for ridge regression, it tries to get better performance or accuracy for the linear model, but it doesn't try to fix the size of the coefficients to be 0. All right, so for elastic nets, actually, I have also done this in the lecture note, but I think it's better that I leave it as additional exercises. So you can try use elastic net to solve this problem. All right, you can look at the last exercises, the last exercise of this lecture note. Just use elastic nets right here. Replace lasso, right? Everything here. Replace lasso by elastic net, capital E, capital N. Right? You can search for how to use elastic nets online. When you search for sklearn elastic nets, right, it will let you know the usage of this function. Or nothing is much different. I think that's all I want to say about lecture 2. And that's all for lecture 2.